Let's talk about multi-unit processes. First, I want you to pause the video and watch another video describing a large coal-fired power plant. The link is below. Now that you've watched that video, I want you to think about the following questions. So industrial processes, like a power plant, often contain multiple units. What are some of the unit processes in the coal-fired power plant? Is this power plant at steady state or is it transient? Is the power plant an open or a closed system? And what are some inputs and outputs? Finally, what are some of the environmental controls that have been put in place? I want you to pause the video and write down your answers to these questions. So the coal-fired power plant is an example of an industrial process that contains multiple units. When you're analyzing a complex multi-unit process like this, you can define many different systems. A system will be a portion of the process that you enclose in a hypothetical boundary. You can do this for any of the following: the entire process, one or multiple units, and piping junctions. Each of these systems, on each of these systems, you can perform mass balances. So here's just a quick example. Here we have two inputs, 1 and 2, going into unit 1. Some sort of waste is made. A third input is added to the stream leaving unit 1 before it enters unit 2. Unit 2 makes another waste, and then the product splits off, and we have two product streams, which I called 1 and 2. So you can draw multiple system boundaries for the above multi-unit process, including around the entire process. So for that one, your inputs would be input 1, 2, and 3, and your outputs would be product 1, product 2, waste 1, and waste 2. You could draw a boundary around unit 1, which has inputs 1 and 2, waste 1, and then an output stream. You could do the same around unit 2, and you could even do it at the mixing point where input 3 is added to the output of unit 1, or the splitting point where products line 1 and 2 are separated. Each one of these boundaries defines a system with different inputs and outputs, and you can perform mass balances on each one of these little systems that you determine. At the end of this video, you should be able to do the following. You should be able to define multiple systems within a multi-unit process. You should be able to perform mass balances on each of the defined systems. And you should also be able to solve mass balance problems on processes with recycle and bypass streams. So one other thing about multiple unit systems is that they can also have these bypass or recycle streams. Recycle lines return a reactor output to the inlet of the reactor. This enables the following. It enables reusing a reactant that hasn't been completely consumed, regenerating and reusing a catalyst or absorbent. It could be used to maintain biomass in a biological reactor, or it could dilute an input stream or control some sort of process variable. In a water treatment plant, you might recycle activated carbon adsorbent through a process until all of its surface area is exhausted. In wastewater treatment, you might recycle sludge or biosolids. These are microorganisms that break down contaminants in wastewater. And here below, here you'll see an example of what a recycle line could look like in a process. So here we have some sort of input going into our reactor, and then we have some sort of separator that separates whatever we want to recycle from our product. When looking at this recycle line, it can be very mind-boggling to think about how we would do a mass balance on this system. However, you can solve these types of problems by performing a mass balance on each reactor and at the mixing point, which I've highlighted here in green. In problems like this, it really helps to break the process down, draw boxes around your systems, and think only about the inputs and outputs to the system you've defined. In a bypass, a fraction of the input is diverted around a reactor. Bypasses may be used to control output compositions or process variables. So this is a schematic of what a bypass might look like. So we have our input going into a unit, and part of the input is diverted before our unit, and then it is mixed again with the output from that unit. So for problems containing a bypass stream, you can solve them by performing mass balances on this mixing point here and the splitting point, and then around the reactor itself. Again, for these problems, it really helps if you break it down into these systems and just look at the input and output, because sometimes just thinking about bypasses can get confusing. So I think it's also important to note that each of these types of systems, that is systems with bypasses and recycle streams, can be at steady state. That is, process variables like concentration in various parts of the system aren't changing with time. So to illustrate these topics, I want to show you an example of a mass balance on a multiple unit process. So I'd like for you to pause and just read this problem. So first, you'll see that this is talking about reverse osmosis. So this is basically a process where a membrane separates pure water from dirty water. So this diagonal line is the membrane. Our feed comes in this case from the left. Permeate is water that has traveled through the membrane so that it's clean, and then the concentrate is what's left over. So it is quite dirty. So what I've done here is I've got a diagram of the process, and you can see that for each stage I basically, I have the flow rate and then the concentration. In this case, we're really just worried about total dissolved solids. What I'm going to do first is I'm going to be looking at something called process specifications. No, sorry. So first, what I need to figure out is how many equations do I need? When I look at this diagram, I can see that I have 15 unknowns. So that means I need 15 equations. I'll start first with process specifications. So these are things that you would see in your problem statement. In our case, it's that each stage removes 96% of the salt, and that these RO units operate with 80% recovery. So I've got an equation here, C3, which is our permeate, is going to have only 4% of the salt, and the same goes for C6. And then I know that the volumetric flow rate of 3 is going to be 80% of V dot 1, and then that V dot 6 is going to be 80% of V dot 2. So those are my process specifications. Now basically what I need to do is go through and figure out all of my material balances. So remember, we can do material balances on so many different parts of this system. We can do it on reactors, we could do it on splits and mixing points. We'll start with A. So this is this first split after the water comes into our system. So basically we have our flow rate in is going to equal the flow rate of the bypass plus V dot 1. So this is basically a material balance on water. Because it's a split, I know that the concentrations aren't going to change. We're basically just dividing this into two parts. So CB is going to equal CN, and C1 will equal CN. Next, what I'm going to do is I'm going to go to stage 1 for RO. And I'm going to do balances on the water and the total dissolved solids for stage 1. So for water, what we see is that the flow rate in, which is V dot 1, is going to equal the sum of the flow rates out, which are 2 and 3. And I can do the same for total dissolved solids. So the mass here of total dissolved solids will be the product of the volumetric flow rate and the concentration for each stream. Now I'm going to do mixing point B in the same way, except that this isn't a split, it's a mix. So I'll do it a little differently. The volumetric flow rates are the same, so the flow in, which is V dot B and V dot 3, is going to equal the flow out, which is V dot 4. And then I'll balance all of the total dissolved solids for the streams coming in and the stream leaving. Next, we'll do RO stage 2. And so basically what we need to do here is do balances for water and total dissolved solids. You're seeing a trend by now, I hope. So our flows into the RO unit will equal the flows out. And same with the mass for total dissolved solids. So mass in equals mass out. And then finally, we'll do this mixing point at C. So basically the volumetric flow rates into that point will equal the volumetric flow rates out of that point. And then we can balance the concentration. So the concentration times the volumetric flow rate for each stream coming in will equal the sum of the streams leaving. So now I have my 15 equations. That wasn't so hard. So now we're going to go about trying to solve these. And I think that the most important part is to just be really systematic in how you solve these types of equations. When you're solving a system of 15 equations, you need a plan. So first start with any equations that only have one unknown. We can actually go through all 15 like this. If you were to do that and you would still have more equations that had two unknowns, then you would need to start, you would need to do pairs of equations with the same two unknowns. And then just kind of move up in difficulty from there. But for this case, we will only be solving individual equations with one unknown. So I'm going to move from the left to the right of the diagram again, and I'll start with this split at A. So basically I know the volumetric flow rate in and the volumetric flow rate of the bypass, so I can calculate V dot 1, which is 12,000 minus 3,100. Now I can use these relationships for the concentrations at that split because the concentration doesn't change at a split. Next, I'm going to do this RO stage 1. But what I need to do before I can solve the material balances is I need to address those process specifications for concentration and flow rate. So first I know that C3 is going to be 4% of C1. And I also know that V3 will be 80% of V1. And I always like to kind of solve these equations and then plug them into my diagram as I go along. That really helps me stay organized. It also helps me kind of visualize where I need to go next when solving a whole bunch of equations. So now I can balance the waters. I know that V2 will be V1 minus V dot 3. And I need to balance the concentrations to find C3. So I'll just rearrange this equation. C3 equals V dot 1 C1 minus V dot 2 C2 divided by V dot 3. And so this is just a matter of plugging and chugging. And so I'll get 5,324. Now just looking at this, you can see that my concentrate stream is much more concentrated than my permeate stream, and it also has a lower flow rate, which is what you would expect given the process specifications. Now I'll do the mix at point B in order to solve for V dot 4 and C4. Basically, we're just going to add those two volumetric flow rates from V dot B and V dot 3 to get V dot 4. And then I need to solve for the concentration by rearranging equation number 11. So I've got 364. You can see that's between 44 and 1100 milligrams per liter, which is what we would expect with a mixing point. Next, I'm going to do this stage 2 of the reverse osmosis. I'll do this just like we did stage 1, where I'm going to need to start with the process specifications. So I'll calculate C6 because I know that it's 4% of C2. And then I'll calculate V dot 6 because I know that it's 80% of V dot 2. And then I can go to my mass balance equations for stage 2 RO in order to calculate the volumetric flow rate V dot 5, which is just going to be V dot 2 minus V dot 6. And I'm going to have to use the mass balance equation, number 13, in order to solve for C dot 5. So basically what we're doing here is we're going through each of these RO stages, and we're using those process specifications to get the concentrations and the flow rates of the permeate stream, and then using mass balance to get the concentration and the flow rates of the concentrate stream. So what we're actually going to see here is that C5 is a very, very, very concentrated. And that's because our influent for stage 2 RO was already quite concentrated. So having a concentration this high would be potentially an issue. So finally, we're going to do our mixing at point C. We're just going to do those balances on water and on total dissolved solids. So we'll add V dot 6 and V dot 4 in order to get V dot 7. And then we'll do our concentration equation in order to calculate the concentration at C7. And so what we see overall is that in this system, So what we're going to do is now we're going to double check. So what we're going to do is we'll double check with mass balance on the entire system. So basically we're going to go back and we're going to look at, we've got our water coming in, at v dot in, and then we've got v dot 5 and v dot 7 leaving. And we find that both of these equal 12,000 meters cubed per day. And then we'll do a balance on the total dissolved solids in the system, looking at the mass coming in through v dot in, and seeing if that equals the mass of total dissolved solids leaving through 5 and 7. And what we see is that actually both sides of those equations equals 1.32 times 10 to the 7th. And so that works out. So when you're looking at something like this, at first it can seem very, very, very complicated. And I mean, it is complicated, but the individual math problems are not that bad. What's most important for these kind of problems is staying organized. So you need to make sure that you draw your flow chart correctly, that you label each stream with a mass or volumetric flow rate, concentrations. Then you just need to systematically go through your system and do mass balances at mixing points, splitting points, and across reactors. And check the process specifications or any other way to get equations, which we'll talk about elsewhere. And you should be able to find the right number of equations. Make sure that number of equations equals number of unknowns before you worry a whole lot about trying to solve the math problem. Yeah, so stay organized and have fun solving multiple unit system problems.